Um, Hello, I wanted to document a recent project of mine, and I know it's a bit messy, but it's this circuit right here. How this works is it can solve the falling body problem. This one, potentiometer here, initial velocity, this potentiometer here, initial position, this one is the force of gravity. This is the first integrator, this is the second integrator. It's on this chip actually, and the capacitors you see on both sides, but these set the initial conditions. Now, most people think computing is inherently digital. It's not. It's really analog, meaning there's a continuous range of voltages, pressures, temperatures, what have you, and then these are, put into regions. We'll say if it's less than 1 volt, that's 0. If it's more than 4, that's 1, and that's how digital works. But it raises the question, can you compute in a different way, using the analog voltage itself to represent the quantity? And that's exactly what this does here. These are voltage dividers with the follower amplifier and 2 numerical integrators. Now we go over to the computer screen. So you see the output is currently a horizontal line on this scale, which is actually, this value here is some, let's see, we can zoom in on there, it's 5 volts per division. That's positive 5 volts provided by the power supply. Now I'm going to start the system. In its resting state, it just applies the initial condition. But when it is triggered, wait a minute, you'll see the output of a solution of a differential equation. So you can see, if that window were larger, you would see a parabola. The body would be here, it went upwards, and then back down, because of course it has a non-zero initial velocity which forces it upwards, and the gravity term which leads to the parabolic behavior in time. I will now write the equations for these. Just give me 1 second. So this is an elementary physics problem which is taught in any physics classroom in the United States. Nearly. The problem takes on the following form. So if we, let me zoom out here real fast, sorry about that. If we want to describe the motion of a body, we have to use Newton's second law, force equals mass times acceleration. And Newton also knew the force of gravity was equal to a constant, which is negative 9.8 times the mass, and this would be in kilograms, and this would be in newtons. Newton, again, he was a bright guy, and so naturally, if we assume there's a falling body, then it has this force acting on it. So that therefore the force is going to equal negative 9.8 times the mass of the body, which is also going to equal, again, mass times acceleration. And so we can solve A by dividing by m on both sides. So it appears this is the acceleration due to gravity, 8 meters per second. Naturally, this involves some calculus because we have the acceleration. Now, generally speaking, if we have acceleration and we take its indefinite integral at dt, then this will give us the velocity function. But that's still not good enough because velocity is not position. If we go one step further, then we have the position with respect to time. Of course, this would have a plus c on it. I'll get to that in a minute. This would be vt dt plus c. This is c1 and this is c2. So let's do this with this constant here. So the velocity would equal negative 9.8 t plus c1. Then we would feed this equation into this equation, and excuse me, and we would get the following form of the, I'll move this keyboard here real fast, the following form of the position function, which would be position equals, with respect to time, would equal, well, it'd be negative 9.8 divided by 2t squared plus c1t plus c2. So this is, you take this and you integrate that, which naturally leads to this form here. Now this constant is called the initial velocity. This constant is called the initial position. This is the equation with respect to time. And so naturally, if we were to draw out the solution, and we had, since this term is always negative and this were a positive term, it's possible to get a trajectory that looks like this, roughly, and that would be parabolic in nature. Now you might wonder, how does the circuit work? How does it take an equation of this form and actually make it appear in the oscilloscope screen? Now on the oscilloscope, time is in this direction, and this would be position. And it's actually more simple than you might think. Let me flip the page real fast here. It's possible to make the following body problem solved very simply. So you have an integrator, right? And this would be the negative, and then this would be, in this demonstration, this is 1 meg and this is 1 microfarad, so that the computer's time is real time. And of course, as always, this is the ground. And then this would go to a second integrator. I'm sorry this is messy. I'm pushed for time this evening. I just wanted to document this. Now this one is still 1 meg, and this is still 1 microfarad. Well, this integrates twice, and then this would be your output. Alright, and so now this configuration integrates twice. And so you would put, because this one does the negative integral and this one does the negative integral, people used to draw these in analog computing manuals like this. And then you'd have, of course, again, these two negatives invert, so this would still be negative G, which would be, we could provide negative G by a voltage divider configuration. This would again be the most positive voltage in the machine, this would be the most negative voltage in the machine. This one is actually about 12, this is minus 12, and this would be set by this potentiometer here. And then this would give you position, which is actually indicated here. Now the trick is, the capacitors at t equals 0 must have a voltage constant. Let me turn off the space heater here real fast. It's hot as heck in here. They must have a voltage constant across both of them. And actually, the voltage constant, which is provided by the two relays I've shown in the circuit, this voltage here at t equals 0 is related to C1, and this voltage here is related to C2, which are respectively initial position and initial velocity. So this one, considering this is an inverting integrator and this is inverting that, this would be negative the value of C1, which is applied across this capacitor for just a moment. And again, this would be negative, I'm sorry, this would be negative, no, this would be positive C1 because that's inverting the second stage. So plus C1, and then this would be, no, again, I'm mistaken. This is actually negative C1, which is that value, and this is negative C2, positive C2. And again, initial velocity, initial position. And so this is a analog model, and again, you'd have to have a system which would control these. So you would have to have like a run reset to this. And again, an oscilloscope or a pen and ink voltmeter would be used to be used to read these off. The fascinating thing is, this is only a half a dozen components. It costs a little bit, nothing too terrible, $20, $30, $40. And so, but the circuit is simple, but the behavior is very interesting, because we can alter the parameters to get different results. So let's reset the system. Wait for it. Like, let's assume we turn gravity to 0 here. Now, in order to do this, I'll reset the position. Well, actually, it's running now. You can see it, the hyperbolic trajectory. And let's assume we turn gravity to almost 0. So let me just swap the lead here. Alright, this is the gravity parameter on the machine. Damn it. There. That's what gravity is represented as a machine, about -7 volts. But let's assume we turn gravity almost to 0 here. Let me adjust this. Again, you can adjust it in real time, which is interesting for differential equations. Usually it's much more difficult than that. So it's making it more negative. Let me just put this down here and adjust it real fast. Okay, there we go. Now gravity here is next to nothing. You can see how close it is to the center line. Wait for it. Right there. Okay, now I will see. I'm actually manipulating this board here as we speak. Then I'll take this scope lead, put it back to the output of integrator 2, which is actually right here. Again, I'm sorry this is messy. I don't have time for too great workmanship. I'm finals and whatnot coming up for tech. Now we reset the initial condition by disabling this, and you can see the output change in response. And now let's see what happens. So now we will turn it on, and you can see it grows larger and larger and larger, and then it slowly begins to fall, but not nearly as quickly as it did. And if we were to cut the velocity, initial velocity, again, this is the initial velocity, initial position, and the gravity term, which are continuous variables. If we were to alter any three of these, we can make it just fall straight down, like objects in a room, or we could make it have a hyperbolic trajectory, or hell, you could make gravity negative so it actually turns like that. And the interesting thing is, although analog computers are not the most precise in the world, this is a relatively simple system for a rather complicated, and again, you have to have initial, which would equal -C1, initial equals -C2. It's a relatively complicated system in terms of equations, but it's relatively simple in terms of a circuit, and it can do something which would be hard to do on a digital computer almost, trivially. If analog computing had the accuracy of digital computing, every computer on Earth would be analog, and I think I can say that with definite assurance. But I'll make further videos. I just wanted to document the project. I hope it was informative. Again, this is the power supply providing +12, -12 and ground. The MIDAC, which hooks up to this computer here to read off the values, and these are LF412 op amps with 1% components. And thank you for watching.